I decided yesterday to take one more look at bonus quiz 2. Made a couple of additional changes just to try to make it sharper and clearer. And added a question. So please take a look at the very latest version of bonus quiz 2. I promise I won't change it again. Now, let's finish with the qualitative aspects of electrochemistry, specifically deriving equations for half reactions, and as necessary coupling them to get net cell reaction. So that we can then proceed into the quantitative aspects of electrochemistry and provide additional significance as to the meaning of E0 and E, which is the operating potential for the cell under any set of conditions, where E0 and E are proportional to delta G0 and delta G. In any case, before we do that, as I believe we noted yesterday, for question 2215, parts 10, 11, and 12 each followed directly from the redox demonstration. So you should have no trouble, I hope, in writing the half reactions and as necessary net redox reactions for those systems. So we'll go to part 13, which again many of you looked at. But I think it's beneficial to us to take another look at this, just to reinforce your ability to deal with such. Automobile battery. A chemical system which I expect all of you own. Chemically, the automobile battery is very simple, because it is made from lead dioxide, with the electrolyte being 4.5 molar sulfuric acid solution. That's it. So chemically speaking, this is a 3-component system. Lead dioxide, and this, the electrolyte. If then we recognize that lead sulfate is produced at each electrode, the anode as well as the cathode, let's derive the half reactions and then get the net cell reaction, or the chemistry that occurs in the lead storage battery. Anode, electrode at which oxidation occurs. We have 0 oxidation state lead, and if lead sulfate is produced at each electrode, then at the anode lead must be oxidized to lead sulfate. Well, the only source, the principal source of sulfate ion in the system is hydrogen sulfate ion. So developing the equation for the half reaction at the anode begins with this. Cathode. In lead dioxide, we have lead in the +4 oxidation state. Given again that lead sulfate is a product at each electrode, lead dioxide must be reduced to lead sulfate at the cathode. And again, since hydrogen sulfate ion is the principal sulfate source, to make lead sulfate, we've got to have hydrogen sulfate ion as a reactant. That's part of the cathode half reaction. So here's what we start with. Keep in mind, when, for example, you deal with exam number 3, for games like this, I have to supply you with enough information to allow you to determine what reactants are and what products are for the half reactions occurring at the electrodes. Without that, you couldn't possibly get at deriving overall net redox reaction. Okay? Now then, as this statement stands, what does it tell us? It tells us that this hydrogen sulfate ion is torn up to make sulfate ion available to react with oxidized lead to make lead sulfate. H plus has got to go someplace. Where does H plus go in any chemical system if H plus is liberated to the system? We've done this many times. It always goes to the strongest base present in the system, present in appreciable amount or concentration. And we know from the PSI for this system the base is water. So, I'll get this out of the way. So we've got room to write water as a reactant. Which becomes hydronium ion as a product since water gobbles up the liberated H plus. That's it for material balance. Charge balance, -1 here, +1 here. So we must have an electron multiplier of 2, showing that we now have a net charge of -1 on each side of the reaction arrow. And as we've already noted, multiplier on electricity always keeps with total change in oxidation number. Lead 0 oxidation state is oxidized to lead +2 oxidation state. That takes care of that. Cathodes. We'll get this out of the way so that as necessary we got more room to write. Hydrogen sulfate ion again is torn apart to make available sulfate ion to make the lead sulfate product. Where's the H plus going? In addition, as this half reaction presently stands, we've got 2 -2 oxidation state oxygens, oxide ions. Remember, this is lead dioxide, which are going into the system. And we know that oxide ions are potent bases, the strongest bases appearing in our acid base table. What's going to consume these potent bases? The best acid in the system. Best acid in the system? But keep in mind that as this reaction runs, we are also putting into the system the strongest Bronsted acid, period. What is the strongest Bronsted acid? Period. H plus. Remember the H plus that comes from this? So, regarding these 2 -2 oxidation state oxygens, how many total protons do we need to clobber these 2 -2 oxidation state oxygens? Keeping in mind that this solution is acidic, and when we clobber oxide ion in acidic solution, the oxide ion will be converted to what? Water. So, 2 -2 oxidation state oxygens, each of which will be converted to water. How many total protons do we need? 4. 1 comes from this. So for this half reaction as reactants, we also need 3 moles of hydronium ion. 1 mole of protons from this, 3 more moles from 3 moles of this, which means we make How many moles of water? Three hydronium ions got deprotonated. That made 3 moles. 2 oxide ions got doubly protonated. That made 2 more moles. Remaining task, establish charge balance. 3 moles plus, 1 mole minus, no charge here. So sum total of charge on the left has got to be 0. Up. So the electron multiplier is 2. And again, that keeps with total change in oxidation state, oxidation number. Lead dioxide, lead +4 oxidation state. Lead sulfate, lead +2 oxidation state. Now, I guess I could have wrote this up there, because we didn't really need any more lines to develop the half reaction, any more space, but we'll leave it like it is. Because I don't want to take time to rewrite it. 2 moles of electricity liberated, 2 moles of electricity required, so we're ready to add them up. Now for this addition, I purposely did no canceling as I added. Took all the moles of reactants from the anode half reaction and all the moles of reactants from the cathode half reaction and put them in a net reaction equation. Similarly, I took all the moles of products from the anode half reaction, all the moles of products from the cathode half reaction, and put them in the net redox reaction equation. Now, can we do any canceling? Can we simplify this net redox reaction equation? This question is inviting you to think more about an operating electrochemical cell which serves the purpose of giving us usable electrical energy. Do you remember that for such a cell to operate properly, reduction and oxidation must be physically separated from each other, because if they are not, you have a short circuit. Okay? The way we've shown you this demonstration-wise, or note or textbook-wise, is with the separate beaker system. If you look at a diagram of the lead car battery in operation, which you can see on Google or any textbook, whatever have you, you will not see 2 beakers or anything like this. If you take your automobile battery out of your car and saw it in half, you'll see there's only one solution system in there, not 2. Does this mean that in the lead storage battery, oxidation and reduction are not physically separated? No, they are physically separated. point. If the materials that are actually involved in oxidation and reduction are not in contact with each other, the cell will function properly to give usable electrical energy. How is it for this system that we can recognize that the materials actually involved in oxidation and reduction are not in physical contact with each other? Lead, solid. Lead dioxide, solid. And reduction product, lead sulfate. Oxidation product, lead sulfate. Point. These materials are not in solution. They're not in contact with each other. You will see, if you look at this diagram for the lead storage battery, that lead and lead dioxide are not in contact with each other. But you don't need to separate the solution part of what goes on at the electrode at the electrodes from each other. Because the solution part, in this case, does not contain the stuff that gets reduced, nor does it contain the stuff that gets oxidized. Now, I will admit, when I first wrote the information that you see in the notes on page 2218, I neglected to realize this about the lead storage battery. I neglected to realize this about the example reaction which I gave you. You see the reaction on page 2218? Zinc, water, hydroxide ion, iron 3 hydroxide, products iron, metal, zinc hydroxide, and hydroxide ion. Don't need to separate the solution components of each half reaction system from each other for that system either. Because the reducer is zinc and the oxidizer is iron hydroxide. They're both solids. As long as they don't touch each other, you don't have a short circuit. That's what I fail to realize. But we'll look at cases where, when we write a net cell reaction like this, if you have hydroxide ions as reactants and hydroxide ions as products, you may not be able to cancel them. Now, I know right at the moment, you're likely saying, what the hell's going on here? I don't understand it. I am sympathetic with that. So I will say, wait until we look at a case where you'll see the physical separation of the solution components is required. Not here. I didn't see that myself when I wrote this the first time. Now then, what that means is we can take this net cell reaction and simplify it. It doesn't matter for solvent. Now, hydronium ions, as things stand, 3 moles reactants, 1 mole product. Simplify that. As things stand, lead sulfate product, not in solution, we could put them together. Hydrogen sulfate ion, reactant, hydrogen sulfate ion reactant. One part of the anode half reaction, the other part of the cathode half reaction. But this is not a participant in the actual oxidation and reduction process. So I can put a multiplier here of 2 and take that out. Now, I really didn't take it out, I just combined it. So all I've done for this case is to simplify the net cell reaction so that it now reads as this. But as I said, in a short while, hereafter, we'll see cases where you can't play the simplification game. So we'll talk more about that when we get there. One more piece of information about this is the operating potential for the anode half reaction. We squeeze this in there. Is plus 0.36 volts. The operating potential for the cathode half reaction, that's this one, plus 1.68 volts. So, for this cell component of the lead storage battery, what's the operating standard potential? Well, we add up 0.36 volts to 1.68 volts and get E0 cell equals plus 2.04 volts. About 2 volts. Do you know the operating potential for your car battery? What is it?
Volts.
What's the operating potential for your automobile battery?
12 volts.
12 volts. Now this is E0 for a single cell in the lead car battery. Question. The lead car battery is composed of how many cells?
6.
How about that? 6 cells hooked up in series. 6 times 2 gives you the 12 volts. Now then, take a look, if you will, at question 2217. For now, neglect 2216. In fact, 2216, you can strike it. Just take question 2216 on page 2218 and strike that. Let's look at question 2217. In discussing question 2215, which as you have seen is composed of many parts, 13 parts. You have a lot of information about relative strengths of different materials as reducers, relative strengths of different materials as oxidizers. That's what the parts of question 2217 are about. How about these two? Well, what if we are going to ask you to compare sodium versus zinc as reducers? Well, what did we discover? Sodium and water, vigorous to violent reaction. The sodium readily reduces the water. Zinc and water, nothing. Sodium, potassium. How do you expect potassium to compare to sodium reducer strength-wise? Potassium and sodium. Which of these do you expect to be the stronger reducer? Hint, you did this in 2045. In what way did you do this in 2045? What's this? First ionization energy. That corresponds to the energy associated with sodium losing an electron or potassium losing an electron. You learned about trends in first ionization energies, didn't you? What's the general in-family trend for A-family elements? Lithium, sodium, potassium, rubidium, cesium. How does the first ionization energy for these elements compare? Say louder. You're going from bottom to top within the family. The first ionization energy value is getting larger. That's correct. Which means if you turn it around, if you go from the top of the family to the bottom of the family, the first ionization energy is getting smaller. In other words, as you go from the top of the family to the bottom of the family, it's easier to get the atom of the element to lose an electron. Okay? What's that tell you about K versus Na, reducer strength-wise? Because when sodium behaves as a reducer, when potassium behaves as a reducer, it involves sodium losing an electron to become sodium ion. Or potassium losing an electron to become potassium ion. Well then, which of these is the stronger reducer? The first ionization energy requirement is getting smaller as you go from the top of the family to the bottom of the family. So this is easier to ionize than this. And when these behave as reducers, they're getting ionized, aren't they? Aren't they converting to +1 ions? Well then, this has the lower first ionization energy. This is a stronger reducer than this. So if sodium is a much stronger reducer than zinc, and potassium is a stronger reducer than sodium, it's got to be a stronger reducer than zinc. This all right? Hydronium ion is a stronger oxidizer than nitrate ion. What information considered in question 2215 allows us to make the statement that as oxidizers, hydronium ion stronger than nitrate ion? Take a look at part 11. Question 2215. Take a look at part 11. Zinc in 6 molar sodium nitrate does nothing. During our redox demonstration, what do we find out when we put a strip of zinc in 1 molar sulfuric acid solution? Zinc was readily oxidized by hydronium ion. Enough said. 6 molar nitrate ion does not oxidize zinc, but 1 molar hydronium ion does. Now, in addition, what did we find out if we've got hydronium ion and nitrate ion together in the same system? Now, what can you say about the oxidizing strength of the system? Did we, in the redox demonstration, consider the possibility of oxidizing copper with hydronium ion? We get any place with this? Nope. But copper in nitric acid solution, that went great guns. Well then, the hydronium ion nitrate ion combo is a potent oxidizing system, more potent than hydronium ion by itself. We've got the results at hand that keeps with this. Because when you tear apart nitrate ion by breaking NO bonds, and in so doing put -2 oxidation state oxygens into the system, you will foster that process significantly if in the same system you've got a strong acid which is ready to gobble up oxide ions as they are produced, like hydronium ion. And then part C, silver, 1 molar hydronium ion, no reaction. Therefore, or I should say, the question as it is asked is saying, silver cannot be oxidized by 1 molar hydronium ion. You'll get no reaction. Why is it fair to conclude that silver cannot be oxidized by 1 molar hydronium ion? Let's write this better. Ag not O by 1 molar hydronium ion because let's write it this way. Silver plus hydrated copper ion gives no reaction. Now, if silver and hydrated copper ion gives no reaction, how must silver and copper compare as reducers, strength-wise? Silver plus hydrated copper ion, nothing. Well, if this gives nothing, what would happen if we put copper metal with hydrated silver ion? Two potential reducers, two potential oxidizers. If this reducer cannot reduce the conjugate oxidizer of this reducer, then how do these compare, reducer strength-wise? Which one's got to be stronger? Which one's the stronger reducer?
Copper is a stronger reducer.
Copper's got to be the stronger reducer. These can't be the same strength. So if this reducer will not reduce this oxidizer, since this oxidizer is the conjugate oxidizer of this reducer, then it must be true the conjugate oxidizer of this reducer, this conjugate oxidizer, is a stronger oxidizer than this conjugate oxidizer. A lot of language involved in this, more than we'd like. But what this amounts to is, if I take, say, 1 molar copper sulfate solution, and in here I put a silver strip, Nothing. No reaction. However, if I take 1 molar silver nitrate solution, and in here I put a copper strip, immediate reaction. Copper will immediately be oxidized to hydrated copper ion, while silver ion in the silver nitrate solution will be immediately reduced to silver and deposit on the surface of the copper strip. And we talked about this. This is the way you'd find out. If you've got any two elements, you want to know how they compare as reducers. Right? You take an oxidized form of each element, do the necessary experiment. Element A, element B. Element A in contact with the conjugate oxidizer of element B. Element B in contact with the conjugate oxidizer of element A. In one of these systems, you've got to get a reaction, which will immediately tell you which element is the stronger reducer and which conjugate oxidizer is the stronger oxidizer. So back to this. If we have discovered that copper is a stronger reducer than silver, and copper, we just talked about this. In hydronium ion. In fact, we considered 9 molar hydronium ion with 9 molar sulfuric acid solution. We get a reaction out of that? No. Well, if copper can't reduce hydronium ion, then silver certainly can't reduce hydronium ion, because we've found out that silver is a weaker reducer than copper. So all this, if Tom is taller than Sam and Sam is taller than Bill, then you know how Tom and Bill compare height-wise. It's the same game. Same thing. All right. Electrochemical arithmetic. In the main, there are really 2 parts to electrochemical arithmetic. Faraday's law and the Nernst equation. I'm going to ask the discussion instructors to wrestle with the Faraday's law parts of this puzzle tomorrow in discussion class. So we are going to go straight to the Nernst equation. Which begins on page 2221. Where does the Nernst equation come from? It comes from this for standard conditions. And it comes from this for any set of conditions. What are the puzzle parts of these relationships? What's N? Moles of what? Moles, electrons, transferred. comes from net cell reaction. F is the Faraday. The Faraday is simply a quantity of electrical charge named in honor of Michael Faraday, a real brilliant chemist and physicist long time ago, who determined much of the fundamental stuff which underlies these considerations. Equals charge on 1 mole of E minus. Did you in 2045 talk about the Millikan oil drop experiment? Remember that? What was the Millikan oil drop experiment about? You talked about it. You don't remember what it was about? Robert Millikan, 1908, University of Chicago, got a Nobel Prize for this work. Anybody remember what the Millikan oil drop experiment was about?
It was about electrons.
What about the electron? Had something to do with electrons. Anybody remember what property of the electron Millikan determined with the oil drop experiment? How much? What? Charge on the electron. Yeah. 1.6 times 10 to the minus 19 coulombs. Yeah, not much. But when you got a mole of electrons, and Avogadro's number of electrons, then you got a quite significant amount of charge. That's the Faraday. The unit of charge is the coulomb, abbreviational reference cap C. And charge is equal to current, the magnitude of current measured in amperes, times the time during which the current flows. Now, E0, of course, is standard electrochemical potential. E is the operating potential under any imaginary set of conditions. From this, we get Nernst in most familiar form. Don't care about the derivation. You're not responsible for that. The derivation's in the notes. It follows from what we've written here. Delta G0 and its relationship to these electrical quantities, delta G, and the value for the Faraday. The operating potential for the cell is equal to the standard operating potential. And then when you put a bunch of information together for constants like the Faraday, you get 0.059 times V volts divided by N, and again is moles of electricity transferred. Times the log of Q. Do we remember what Q is? Q is an expression which is identical to what? K, equilibrium constant. So if you can write an equilibrium constant, you can write Q. The difference is the equilibrium constant corresponds strictly to equilibrium conditions, whereas Q corresponds to any imaginable set of conditions. Okay. Now, go ahead.
The V, is that the units per 0.059? Or,
This is V volts.
yeah, but I'm saying, is that the units or that time? You said that time.
No, it's 0.059 volts divided by moles of electricity. All right? Now then, take a look at page 2222 and 2223 for a moment. The very common use of Nernst equation is to determine K values, equilibrium constants. Very often evaluated by application of the Nernst equation. On page 2222, you see an example of using the Nernst equation to get Kf, where F means formation of the copper ammonia complex ion. Read it if you've not yet done so. Page 2223. Also, very common use of Nernst is to measure pH. In 46 laboratory, for example, you've got simple laboratory grade pH meters. They all operate on the basis of the Nernst equation. Take a look at the table of half reactions right now. That's table 2. I will also take a look at this table at this point. The question is, when you look at table 2, do you see half reactions which could be used as a component of electrochemical system, for which, if we applied the Nernst equation, we could measure pH? Do you see half reactions here which can be used to allow measurement of pH? There are a lot of them, few of them. What do you think? Question. Which half reactions in table 2 can be used for pH measurement? We're going to make an electrochemical system. To this electrochemical system, we're going to apply the Nernst equation. The purpose of this electrochemical system and the application of Nernst is to allow us in the laboratory to measure pH. So you're in the lab. You're an electrochemist. Do you see electrochemical, pardon me, do you see half reactions listed in Table 2, which can be used to serve this purpose? There's a whole bunch of them. What property must be shown by a half reaction if it can be used to permit measurement of pH? What must be a property of the half reaction? What is that?
Hydronium concentration.
You got to have hydronium ion in it, right? What else?
Hydroxide.
How about that?
Water.
It's got hydronium ion in it or hydroxide ion in it. Bingo. You can use it as part of an electrochemical system to which application of Nernst will allow pH measurement. What you see then on page 22-23 is one example of an electrochemical system used for measuring pH. And if you read through this, you'll find out that once you assemble this electrochemical, this is the way the pH meter works in laboratory. The pH meter reads a cell potential for a solution. What's the cell potential for the solution? But the pH meter doesn't give you the cell potential. It does some arithmetic inside the circuitry of the pH meter and converts the cell potential to pH. So the pH meter spits out a pH. That's what you read. You see this relationship at the bottom of page 22-23? That's what the pH meter is doing inside its circuitry. It reads E cell, doesn't give you E cell, it reads the pH. That's the arithmetic it would use if the pH meter was operating on the chemistry described by the cell whose standard notation is given at the top of page 22-23. The zinc ion, half cell coupled with the standard hydrogen electrode. That's what you see at the top of page 22-23. All right. Then on page 22-24, there's some couple of considerations given on what you could do to measure the reliability of your pH meter. We're going to leave that for the actual practicing electrochemists. Let's get on with chemistry. Let's go to question 22-21. And I trust you've recognized, but perhaps not yet, because we have not yet on quizzes or, pardon me, exams, asked you about the Nernst equation. This is on the information sheet. You don't need to memorize it, but you do need to be able to use it. It's like Faraday's law. That's on the information sheet. Your job is to use this stuff successfully. So let's start taking a look at some examples of how you would use the Nernst equation. 22-21. Here's the system. Expressed in standard cell notation form. Last Friday, I believe, in discussion class, one of the considerations put to you was how to write a cell in standard cell notation form. Here's an example of such. What does this information tell me? It tells me the cathode half cell involves the oxidation of zinc to hydrated zinc ion. And this information also tells me that in the cathode half cell, hydrated copper ion is being reduced. It's being reduced on the surface of the cathode, which in this case is a copper strip. So I would be making copper atoms and plating them on a copper strip. That's what this means. Pictorially, what does this look like? We've already seen this, but so that I hope this stuff starts to connect together. Here's a zinc strip. Stick it in a solution of zinc ion. If this is zinc sulfate solution, and we also got sulfate ion in there. You could put sulfate ion in here, but I don't choose to do that. You could write this as ZNS, physical separator, 1 molar ZnSO4. I rather do this than this because this tells me explicitly what the reducer is and what the oxidation product is. And if I've got copper sulfate solution, I could write this as copper sulfate solution. But again, this tells me explicitly that for the system I'm going to consider hydrated copper ion is the oxidizer. So pictorially, here again is what we got. If my cathode material is copper, as it is in this case, we got a copper strip sticking in here. This is hydrated copper ion. And if it's copper sulfate solution, we also got sulfate ion floating around in there. These will be connected for the demonstration purpose we did with a salt bridge, piece of wire, meter, or if we want to put this to practical use, we'll put a socket in here. And there's my $64 Van Gogh representation of a light bulb. Good enough. If it works, there, the light bulb glows. How about that? We've lit the light bulb. Now then, 2221 says, let's consider application of the Nernst equation to this particular electrochemical cell. What's in? Well, we've been through this system before, so I'll go straight to the net cell reaction. For which E0 is 1.10 volts. Remember getting at this before? Because the parts here, zinc, oxidized to hydrated zinc ion, has a potential of plus 0.763 volts. That's in the table of half reaction. And hydrated copper ion, being reduced to copper, has a potential of plus 0.34 volts. So when you add those two values, you get E0 cell. This we've been through before. Diagrammatically, we can represent this like this. Zinc oxidized to this, Hydrated zinc ion plus 0.763 volts. Hydrated copper ion, the copper, plus 0.34 volts. Of course, the copper ion copper half reaction in our table is written in the opposite direction, for which the potential is minus 0.34 volts. But when we couple, when we make an electrochemical system from these ingredients that gives us usable electrical energy, copper ion winds up being the oxidizer, and copper ion therefore gets reduced. So here's what we got. What's N? I repeat, N comes exclusively from the equation for the net cell reaction. If that's the net cell reaction we're using, what's N? How many moles of electricity transferred for this system to operate? 2. 2? Now, what if I put coefficients of 1/2 through here? I still got a legitimate equation. Half mole this, half mole this, half mole this, half mole this. If I do that, what's N? If I double these coefficients, 2, 2, 2, 2, what's N? 4. N comes strictly from the equation for the net cell reaction. As written, N is 2. And here's Q for this system. Question. If I want for this system E cell, if E cell is to be larger than E0 cell, how must the concentration of zinc ion CT compared to the concentration of copper ion? For this system, if I want my operating potential to exceed 1.10 volts, I want E cell to be bigger than E0 cell. How must I operate on the molarities of the two ion components of this system?
That has to be less than 1, so molarity of zinc would have to be greater. Or less than molarity of copper.
Which molarity must be higher?
Molarity of copper.
This molarity has got to be bigger than this molarity. Does that not follow from standard thermodynamic considerations? Does that not follow from Le Chatelier's principle? Here's the equation for the reaction. If I want to boost the drive for this system to go as written, I want to up the molarity of this while I lower the molarity of this. That ups the drive this way. In turn, if I up the molarity of this while lowering the molarity of this, I'm tending to drive this thing in the reverse direction. That's not what I want to do for this system. So what we've done so far is simply to talk about the very fundamental aspects which underlie your understanding of the Nernst equation and how it works. Tomorrow, as I said, you're going to look at use and application of Faraday's law, and you'll proceed with some specific examples of use of the Nernst equation. Be there.